So welcome to my talk, a hat trick of automatically verified representation invariant using symbolic finite automaton. So my name is Zhou. It's a joint work with Qianchuan, Benjamin Delaware, and Suresh Jagannathan, my advisor. So let's just get started from the context. We talk about effectful programs. These are programs that interact with opaque environment. This means that these effectful programs use effectful operators like put and get. And the corresponding implementation of a put and get are unknown. And they probably interact with a database, which is, say, the effectful context who have hidden states. And the problem we want to solve is to verify the program with effectful operators. So the first challenge is how can we express the property of the program that interact with the opaque environment? So as you see, these effectful operators have unknown implementation, and effectful context should have hidden state, satisfy this expected properties. And only thing we can observe is corresponding interaction. And the second challenge is that how can we automatically verify it? Okay, let's move on to the motivating example to see that concretely. We talk about abstract data type ADT mean set is just a set equipped with a minimal element. So it can be expressed as a pair of integer and integer lists, look like this. So the set is a list of elements 2, 3, and the minimal element is just 2. And the min set instance can be manipulated. For example, it can add a new element 4, and we go to another min set instance and have update the set. And if we add a new element 1, both minimal element and the set need to be updated. And all this means that instance need to satisfy the min set property is the minimal element is less than all elements in the list. It's indeed minimal. And the implementation of this add function need to preserve this min set property. So that is our verification task. But how about if we implement the min set add function with effectful operator to achieve a better efficiency, and now we don't have explicit representation. And when we have effectful context has some hidden state. And when we do the add function have effectful implementation and use the effectful operator with unknown implementation. And look like this. We use the write and read to manipulate the hidden minimal element and use the insert to manipulate the hidden set. And the only thing we know is some specification, just a simple algebraic loss over this operator. For example, the return values is equal to the last return one. And we can use the effectful operator to manipulate the effectful context. For example, insert 4, and that is the only thing we can observe is events we call the operator invocations. And the effectful context now will have another hidden state. Okay, here is an example of the code of the add functions implemented with the effectful operators. And you can have the effectful context have hidden states. If you run the add function under this hidden state, and you can say if add element 2, and the first line we try to say if the previous write happens, so just say because we have a minimum element 3, so that is true. And we go to the second branch, we try to read, and we read the element 3 because the minimum element is 3. And because the input element 2 is less than 3, so we need to update the minimum element. So write 2 and also insert 2. And we go to another context. Okay, so the problem I want to say is here, how can we verify the effectful implementation just preserve the min set property? So user need to provide the source code and the min set property and the specification over the effectful operators. And we will try to automatically prove. When we call the add function, if the context is valid with respect to the min set property, and should also end up with the context valid with respect to the min set property. Okay, so for the first challenge, how can we express min set property? Remember that is an effectful context have hidden state. So our key idea is that we represent as just directly as a sequence of observed events, or we call the traces. So for example, looks like this. And we can use this sequence of events as a history to recover the hidden state because we know the last write is 2, so the minimal element is 2. We already insert 2 and 3, so the set contains 2 and 3. Now we have a trace-based property. We have a new version of the mean set. A is, say, you cannot write values that are greater than any previous insert one. And you can say that you use the if-else operator directly. So that's totally independent from the corresponding implementation of the if-else operators. And how can we automatically verify it? We introduce a trace-based type system. We'll statically approximate the produced trace of add function and check if that is consistent with the mean set property, A mean set. Okay, so the rest of talk, following this outline, I will talk a more detailed solution about these two challenges and a concrete application, how we verify the representation invariant. Okay, so before I talk about this, we first introduce the core language. Issued under a trace-based view. So first we have if-else operators, as you saw this before. We have events. Events consist of three parts: if-else operators, the arguments values, the result values. Here's an example of the events. And trace just a list of events. And we talk about the operational semantics in small step cell. Just like a simple lambda calculus, you reduce a term E to an E prime. But in our setting, you need to do that under context trace alpha and produce a new trace beta. And here is an example. That is a context trace. And this is a term. We first do the read. Because the previous is right, we have a result of read 3. And we produce a new trace and go to another term. And the thing you want to remember here is that you need to append the new producer trace to the context trace to continue the reduction. So if you want to reduce a new term, you have this context trace, and the context trace always growing. Okay, so let's move on to the first challenge. How can we express this property? Remember that it's a data-dependent temporal properties. So look at this property. You can see there's a previously, right? So it's actually have temporal property. So we use the linear temporal logic actually on the finite trace. We call the LTLF to express it. So here is example is a formula of this property. And we have a global modality, final modality, and atomic predicate is just an if-else operator. And this formula means wrong-write event cannot appear after a previous insert event. So the LTLF is actually have the expressive powers the same as the finite automaton. And you can have a corresponding automaton looks like this, which translation can label as the if-else operators. We have two. And we say if insert happen, go to another state. And the write cannot happen, so remove this. So that is a corresponding finite automaton. And we see how we can accept the trace. Here's an example of the trace for the first event. We go to here, the self loop. Second event, we go to the second state. And insert the self loop, insert self loop. And this double circle means that the final state of automaton, so we accept it. But we still have a gap. So then we say the wrong write event cannot happen. But what means wrong? We say there's actually something greater than previous insert value. But how can we express the greater than? That is a data dependency. So we extend the linear temporal logic on finite trace to the symbolic one, how to express the data dependency. So we call the symbolic LTLF. That is a corresponding formula. You can see this word is similar, but actually our atomic predicate is now the symbolic automaton, symbolic event. It consists of 4 parts: if-else operators, parameters, and result variable, which constrained by a qualifier phi. So here is a qualifier. You can see there's actually use a greater than indicates a data-dependent property. And symbolic LTLF, the same expressive power with the symbolic finite automaton. And here is the automaton. And now it actually can transition and label as 4 cases and not 2 because we have the qualifier. And still, you can see if you have an insert with element, and you cannot write element greater than element, right? So just remove this case, and that is a corresponding symbolic finite automaton. And still, we can see how can we accept a trace with this element of 2, that's the concrete trace. And the first event, I have a self loop. The second event, go to another state, and self loop, and you can accept it. Okay, the second, so you can see there is an element, it's a free variable in the symbolic automaton. You can check the details in our paper, how we deal with it. So the second interesting point I want to talk about is the context dependency. So consider the add function. The behavior of the add function is actually different under different context trace. So if the minimal element is 1, we don't need to, when the insert 2, we don't need to add, more update the minimal element. But if the minimal element is 3, now we need to update both the set and the minimal element. So it works differently, right? But how can we express this context dependency? So the solution is that we use a Horsell pre- and post-condition symbolic automaton to express it. So it looks like this, and here's a concrete example. This part is a precondition symbolic automaton. The first is still, we say that it's a valid mean set, and conjunct with, we say no value less than the element is written. That is consistent with your context trace. And post-condition symbolic automaton always have a copy of the precondition automaton, and the concatenation with a new producer trace is to say, eventually, finally, we'll write this element. So it's just like you always have new producer trace to be penned to your context trace. Okay, so let's move on to the second challenge. How can we automatically verify this property? So we introduce a whole automaton type we call the hat. The hat is a refinement type system. Additionally, refines a refinement type with a pre and post symbolic automaton. We use a symbolic automaton to express the data-dependent temporal properties, and we use a pre and post condition to express the context dependency. Here is an example of the type of the add function. We have a function type, and the result type have the same pre and post condition that is a mean set property. So that is meaning how we preserve the mean set property. And we also support the high-order effective function. Please check in our paper. Okay, so the next interesting point I talk about is the subtyping check. So how can we do that automatic verification of the type system, just like following the methodology of the refinement types? The bidirectional type check, you have a type, you want to type check with the type, and you first do the type synthesis. You synthesize a term to another type, and you do the subtyping check. And this one can be automatically solved by the assembly solver, and this query are decidable. In the same thing as in the whole automaton type, we also have a type check, and also have a type synthesis. Here we find that they actually have the same preconditional automaton. It means that all the things happen in the same context, but have a different post-conditional automaton. And now subtyping have two things. It's just a standard subtyping and an inclusion check between two symbolic automaton. And still, the first part can be solved as a solver. The second part, we have a symbolic automaton inclusion checker that is still automated and decidable. Okay, so let's move on to the real application, the verified representation invariant. So that's not quite different from our motivating example, because for ADT mean set, the representation invariant is just the mean set property, and we try to verify all APIs, not just the add function, to preserve the mean set property. I will introduce meta theory implementation and evaluation then. So the meta theory would just say, vol type the term preserve the representation invariants. So we type check a term always have the same and pre and post conditions as a representation invariant. Maybe I don't have time to go through these details here, but we have a formalization of it. And implementation evaluation, we implement our type checker called Marple in OCaml, and we use this as an assembly solver and final automaton inclusion checker. So for the evaluation, the first research questions I want to ask is about efficiency. So our benchmarks include effectiveness. Our benchmark includes the 9 ADTs, implement 2 to 3 versions, includes 3 to 7 APIs. It actually support 5 underlying stateful libraries. So it means that we have 5 different set of effectful operators can be used. And the second research question is about the efficiency. So the total type check time of this range from 2 seconds to no more than 3 minutes. So that is actually a reasonable time because that is the total time to verify all APIs of ADT. Okay, so this is a summary. So we introduce a whole automaton type, a novel refined type system, verifies the representation invariant of the effectful program. And we introduce the symbolic linear temporal logic on the finite trees and symbolic automatons to express a data-dependent temporal property, and pre- and post-condition symbolic automaton to express a context dependency. Please check our artifact uses QR code. Thank you. Open for questions.
Thanks for that talk. So do you make any restrictions on the symbolic linear temporal logic formulas to ensure the sort of decidable inclusion checking, or?
So you consider about our logic here, right? So if that is decidable?
Yeah. I mean,
yeah. So Actually, all the things, linear symbolic logic is just a front-end language of S. Eventually, we will combine all the things here to the symbolic automaton. So the decidability is guaranteed by the theory of the symbolic automaton. So that is indeed decidable. Does it answer your question?
Yeah, thanks.
Yeah.
Do we have any other questions? Okay, well, I will ask a question. I actually have a question.
Yeah.
So you have this framework for proving properties of your program about these ADTs. Now, if I have some equations about the ADT, could you use these sorts of proofs to then optimize the code? For example, if I have things about my data structure that tell me that an add and a remove can be canceled out, could you use this framework to then optimize the code based on that information?
You say that is can I use my current framework to do optimization?
Could you imagine as future work to plug this into a compiler to give it that information and allow it to optimize better?
It's very interesting direction. So currently I'm thinking about this as a verification framework, right? So you need to get a concrete source code and a concrete specification. All the things need to provide it. But I think that's a very interesting future work to find if I can optimize this as a source code. Yeah.
All right. Do we have any other questions in the audience?
Yeah.
All right.
Thanks for the great talk. So I'm wondering if your framework can support non-algebraic effect like a control effect, call CC, exception handling, effect handlers, and so on.
So you are asking about can we support like call CC, there's new features besides the current core language? Yeah, so that is actually our future planning, right? So I think this is also very quite fixes the algebraic effects, other things, or is this a delimited continuation? So we are trying to explore it. The things that if after this you have a continuation, right? So how can we say express this continuation as a decidable computation model like a symbolic automaton? So that is a question still we want to not quite clear now. That sounds a question?
Yeah, thanks.
All right. Let's thank the speaker again.